Swayam Prabha. Digital India. Educated India.
Welcome to MSP lecture series on advanced transfer chemistry. In my previous lecture, I had initiated discussion on physical and chemical properties of transfer elements. Let me continue from where I had stopped. If you consider metals such as titanium, zirconium, iron, nickel, copper, silver, gold and platinum, they are used in many ways in everyday life. However, molecular complexes, organometallic compounds, transition metal chalcogenides, I mean solid state compounds and halides are extensively used in inorganic and bioinorganic areas of research, besides their utility in homogeneous as well as heterogeneous catalysis for a variety of organic transformations. Before we little deep into coordination compounds, let us try to understand acid base concept. And hard acids and hard bases have high charge, that means acids have positive and bases have negative charges to size ratio, that means they have high charge to size ratio, and also metals are always in their higher oxidation states, and hard acids are not very polarizable and have high charge densities. Metal ions with high positive charges and smaller ionic sizes tend to be hard acids. That is the reason early metals, when you strip off all valence electrons, they always try to be hard acids and hence they are oxophilic and halophilic. Early transition metal ions of 3D series tend to be always hard Lewis acids. Small anions and neutral molecules tend to be hard bases. If you want to consider examples for hard acids, H plus, Fe3 plus and aluminum 3 plus are examples of hard acids as far as main group acid and bases are concerned. And in case of hard bases, F minus, O2 minus, OH minus hydroxide. Let us try to understand what are soft acids and soft bases. Soft acids or soft bases have a low charge to radius ratio with metals in their low oxidation state. This is exactly opposite to hard acids and hard bases. They are normally larger ions and are polarizable. For example, I minus iodide and S2 minus sulphide are soft bases, and low valent transition metals or metal ions such as silver plus or copper plus are soft acids. Also 4D and 5D metals in their plus 1 and plus 2 oxidation states as well as late transition metals with filled or almost completely filled d orbitals are soft acids. Acids such as trimethyl boron, Fe2 plus, Pb2 plus are intermediate acids, whereas pyridine and aniline are intermediate bases. An element can also change its hard and soft character depending on its oxidation state. For example, let us consider hydrogen. H plus is a hard acid whereas H minus is a soft base. Similarly, nickel 3 plus is a hard acid whereas nickel 0 in nickel tetracarbonyl for example is a soft acid. So, the figures that I am going to show hard soft trends for acids and bases in the periodic table. For bases, the major hard soft discontinuity is between second row, that is for nitrogen, oxygen, fluorine and the rows below. You can see here hard and soft acid and bases I have given here, and if you see the left side of the periodic table and covering almost alkali metals and alkaline earth metals and partly 3D and 4D and 5D metals, they are all hard acids and they have less number of electrons in their valence shell and they exist in their highest possible oxidation states and are hard acids. And if you just look into elements put in blue color, they are all soft acids you can consider here, and whereas in case of donor atoms in blue in color are soft bases, that means soft Lewis acids I would say, carbon, phosphorus, arsenic, antimony, selenium, tellurium, bromine and iodine, whereas nitrogen, sulfur have partial or intermediate character. Chlorine is also intermediate in nature, whereas oxygen and fluorine are hard bases. And here aluminum, silicon, gallium, germanium and tin are when it comes to metallic properties they are soft hard acids. Hard acids interact more strongly with hard bases than they do with soft bases. That is the reason the combination of hard acid and hard base is more stable, and similarly a combination of soft acid and soft base is very stable, but other way around is considering hard acid and soft base, or soft acid and hard base, they are relatively less stable. So, soft acids interact more strongly with the soft bases than hard bases. Hard and soft interactions results in the formation of most stable complexes, and hard acid bind halides in this order, you can see the order shown, whereas soft acids follow the opposite trend. For example, if you consider early metal fluorides are more stable, whereas late metal iodides are more stable. The softest metal ion in the periodic table is gold plus in aqueous solution. It forms stable complexes with soft bases such as phosphines and cyanide, but not with hard bases such as oxide and fluoride. And here I have shown some examples of gold +1 complexes. Here it is linear, and of course we have extensively studied gold chemistry in our laboratory, and we have examples for different geometries of gold. For example, in these examples it is linear, in this one it is trigonal planar, whereas in this case gold +1 state being tetrahedral, and again it is trigonal planar. The affinity of oxygen plus for soft cyanide minus is very high, and hence AuCN twice 2 minus is very stable. That means the gold can be oxidized by oxygen in the air in the presence of cyanide. The affinity of gold plus for soft cyanide is very high, and hence AuCN twice anion is very stable, that gold can be oxidized by oxygen in the air in the presence of cyanide. So, this property is exploited in separating gold from sand and other oxides. For example, you can see when gold is reacted with cyanide, that means basically we are taking sodium or potassium cyanide with water, dissolved oxygen is good enough, it forms this dicyanoaurate anion. This reaction is used in gold mining to separate small flakes of gold from large volumes of sand and other oxides. Silver is similarly dissolved by air oxidation in cyanide solutions, and this is called cyanide process. The precious metals are separated from the solution using chemical reducing agents or by electroplating. Au3 plus ion, gold 3 plus ion, due to its higher charge is harder than gold plus and can form complexes with harder bases such as water and amines, and auric iodide or RS iodide, that is AuI, a combination of soft and soft, is stable, but AuI3, it is a combination of hard and soft, is unknown. That means one hard acid and other one soft base, extreme ones is unknown, similar to PbI4. Similarly, AuF has never been isolated, but AuF3 is stable. AuF3 is stable because Au3 plus is hard acid. The use of cyanide ion on a large scale in mining however creates a potentially serious environmental hazard. Cyanide spill at Baia Mare in Romania in 2000 resulted in the worst environmental disaster in Europe. Highly toxic cyanide is gradually oxidized by air to the less toxic cyanide ion. In laboratories, cyanide plating solutions are typically disposed of by using bleach to oxidize cyanide to cyanate, and the metal is recovered as an insoluble or soluble chloride salt. For example, sodium cyanide on treatment with the sodium hydroxide in presence of chlorine gives NaCnO plus 2 NaCl plus H2O. So, this reaction takes place in the pH range of 10 to 11.5, and sodium cyanate on further reaction with sodium hydroxide or bleach, say sodium hydroxide plus 3Cl2 gives 6 NaCl plus 2 CO2 plus N2 plus 2 H2O. So, this takes place in the pH range of 8.5 to 9, and similarly cyanide can also be neutralized by using thiosulfate, and this process is used in cyanide poisoning in the living beings, and using base should not be considered, and if very small quantity of cyanide poisoning is there, sodium thiosulfate can be used. So, on January 30th 2000, the dam containing toxic waste material from the Baia Mare Aurel gold mine in northwestern Romania burst and released 100,000 cubic meters of waste water that was heavily contaminated with cyanide into the Lapus and some tributaries of the river Tisa, one of the biggest river in Hungary, and because of this disaster wildlife was severely impacted by the Maria Barry cyanide leak, and all living things along that river bank were killed, and in Serbia 200 tons of fish in the rivers were killed and 80% of all aquatic life was totally destroyed. The cyanide leak affected at least 32 fish species in that river. So, you can imagine the kind of disaster we had because of cyanide process and letting cyanide to contaminate river. Okay, let us come back to transition element series. If we look into the first transition series, scandium through copper, 3D subshell is filling starting from 3D1 to 3D9, and you can see irregularities when you go to chromium. So, chromium is supposed to have 3D4 4s2, and similarly copper should have 3D9 4s2, because the electronic configuration listed is slightly different. The reason is, we know the fact that half filled and completely filled electronic configuration gives stability. As a result, what happens, one electron from 4s2 is added to have 3d5 and 4s1 electronic configuration for chromium, and similarly copper assume an electronic configuration of 3d10 and 4s1. So, this is because of extra stability, and of course this anomaly we also see with nickel group where we have D8 and S2 electronic configuration. If you look into nickel, it is perfect, no issues, it shows D8 and S2 electronic configuration, but if you go to 4D palladium just below nickel, it has instead of 4D8 5s2 electron configuration, it has 4D10 and 5s0 electronic configuration, and again there is a difference in the electronic configuration of platinum as well. Platinum, instead of having D8 S2 electronic configuration, it has D9 S1 electronic configuration. That means the electronic configuration of platinum is 5D9 and 6S1. When we look into second transition series, we go through yttrium to silver, and again 4D subshell is filling. Irregularities are observed for niobium, which skips from 4D3 5s2, 4D4 5s1, and palladium, which goes from 4D8 5s2 to 4D10 5s0, that is what I did mention. and irregularities are observed for 4d3 5s2 if you just look into it that also, but in this case there is as such no benefit for the stability, but the reason is not clear why niobium instead of having 4d3 5s2 electron configuration it has 4d4 5s1, probably to facilitate more metal metal bonding, and also when you go for higher orbital the energy difference will be smaller and the size is bigger. As a result these orbitals can diffuse into each other and hence probably this kind of promotion of electron either way should not take much energy, and that is the reason probably electrons can be moving or dissociating or associating easily between the neighboring orbitals. When you look into third transition series lanthanum to hafnium through gold 5d subshell is filling, again irregularities are observed only in case of platinum that I already mentioned. The fourth transition series which is incomplete, okay, actinium to element 104 through element 111 and here 6d subshell is filling, and of course now we have completed the series. This slide shows the electronic configuration of 3d series starting from scandium to zinc. We have D1 system here and we have D10 system. Since all the valence orbitals are completely filled here and zinc do not really follow the trends that are observed among transition elements, and in contrast the chemical and physical properties of zinc, cadmium and mercury are much more related to main group elements. So, metal complexes of 3d series show up to 6 coordination and rarely show 7 coordination. 3d series metals or elements are relatively smaller in size and as a result they cannot go beyond 6 coordination, whereas 4d and 5d series can show up to 9 coordination. For example, there is a tungsten 2 complex shown here. This can have either capped-octahedral geometry or pentagonal bipyramidal geometry, and here coordination number is 7, and in case of this hydride, homoleptic hydride rhenium H9 2 minus, rhenium is in +9 state having tricapped trigonal prismatic geometry, and higher action states are more stable in the case of 4d and 5d metal series compared to 3d series. So, 3d series prefer to have lower action states, whereas metals in 4d and 5d tend to stabilize with higher action states. And of course here the reason is very simple, the size is little larger compared to 3d, as a result valence electrons are little away from the nucleus and as a result it is very easy to ionize electrons in 4d and 5d series. For example, hexachlorotungsten, osmium tetroxide and PtF6, and here tungsten exists in +6 action state, whereas in this one osmium exists in +8 action state, and whereas in this case platinum is in +6 state. So, 3d metals generally show +2 and +3 action states. For example, very few molybdenum tungsten compounds exist in +3 states, whereas chromium compounds are many with chromium in +3 oxidation state, and 4d and 5d metals generally possess higher enthalpies of atomization compared to 3d metals. This is due to the relatively greater metal metal bonding. So, while explaining the radius and also melting point, I did discuss about these aspects. Let us look into the standard reduction potential for some metals in the first period. Some values I have given here, and here if you just see I have included calcium also, and starts with calcium and end with zinc here. As you see the values of alkaline earth metal is negative, that means it can be readily oxidized, and as the value decreases they tend to be more and more reducible in character. That means copper 2 plus can be readily reduced to copper compared to calcium 2 plus getting reduced to calcium in its 0 valent state. And this redox potential is very important when we want to use these metal complexes in various applications. Let us look into this question here: in what way does the value of E naught for the Fe2 plus to Fe couple depend on the first two ionization energies of Fe gaseous. So, that means here one should look into the enthalpy or heat of formation of Fe2 plus, is it comparable with the two ionization energies required to remove 2 electrons from the gaseous iron atom to form Fe2 plus. So, first consider Fe2 plus takes 2 electrons in a reversible fashion to form Fe. So, E naught for the Fe2 plus to Fe couple refers to the reduction process. This is the redox potential I am referring to. E naught is the redox potential. Relative to the reduction, 2H plus it takes 2 electrons in a reversible fashion to form hydrogen molecule. That means the sum of the first and second ionization energies, that is IE1 and IE2, refers to the process FeG giving Fe2 plus. That means you have to take 1 electron for using first ionization energy and apply another second ionization energy and strip another electron to form dication. Now to understand this one, this thermochemical cycle I have shown here. First you consider Fe2 plus aqueous, and when you add 2 electrons it forms Fe, and then Fe on atomization it forms Fe gaseous, and then when you apply first ionization energy and second ionization energy, so you can remove 1 electron at a time to eventually form Fe2 plus, and then Fe2 plus hydration, on hydration it forms aqueous, that means hexa aqua iron 2 plus. So, here delta hydration G naught is the Gibbs energy change for the hydration of gaseous Fe2 plus ion. This cycle illustrates the contribution that the ionization energies of Fe makes to delta G naught 1 here. The Gibbs free energy change associated with the reduction of Fe2 plus to Ag, that is the one. So, this is in turn related to redox potential of this couple. That means you can relate free energy, Gibbs free energy, to this equation delta G naught equals minus Z F E naught, where F is 96485 coulombs per mole, and in this case this is a 2 electron process, Z equals 2. So, using this one for any reaction one can find out delta G, or any missing component can be found out. Let me discuss little bit about the reactivity series before I conclude this lecture. The reactivity series is a series of metals in order of reactivity from highest to lowest. It is used to determine the products of single displacement reactions, whereby metal A will replace another metal B in a solution if A is higher in the series. This information also comes from the redox potential table. So, activity series of some of the more common metals is listed here in the descending order of reactivity, you can see here. And also of course this is the oxidation half reaction I have given, and for comparison I have also included alkali metals and alkaline earth metals, and also main group elements along with some chosen transition elements. And one should give more importance to these signs. This is very important. This will tell about how easily one can be oxidized, or a metal or a element can be reduced or oxidized. And this chart shows the reactivity. For example, whether they react with water, if not they react with acid, or they are not at all reactive. So, let me stop here and continue further discussion on transcendental chemistry in my next lecture. Until then, have a wonderful time reading chemistry. Thank you.